In this section, we will discuss the common elements needed for all power supply designs. We can identify these as four main components: inductors, capacitors, diodes, and MOSFETs. A majority of all power converters utilize a magnetic field for energy storage and conversion. This can be in the form of a transformer or inductor. An inductor is a passive element that stores energy in a magnetic field and resists changes in electric current. An inductor acts like a short circuit at DC voltage and an open circuit at high frequencies. Switch mode power supplies rely on the steady state inductor principle for power conversion. More on this later. There are several inductor considerations to pay attention to in power supply design. First and foremost is the inductance value. Inductance values can be in the tens of nanohenry range for very high switching frequency converters to the millihenry range in very low frequency converters. Common power supply design practice suggests that the inductor value should be sized to produce ripple currents about 20 to 40% of the full load current. DC current rating is the amount of current the inductor can handle in steady state. Typically, this is specified for the DC current that causes a 30 degrees C temperature rise in the inductor due to parasitic resistance in the winding. Saturation current, on the other hand, is the current at which the inductance value drops by 30%. This is a tricky specification because inductors pass triangular wave currents, so the peaks need to be kept within the saturation current limit. If the saturation current is exceeded, the inductance will approach zero, causing the inductor to act like a short circuit. DCR is the DC resistance, which factors into the DC current rating. This number will allow the designer to calculate the DC losses in the inductor. Core loss is energy lost due to changing magnetic energy in the core during the switching cycle, and eddy currents, which are induced in the core material by a time-varying flux. Lastly, the saturation profile is defined by the core material. Some materials, like powdered iron, allow the inductance to fall gradually as the inductor current is increased. Others, like a ferrite, have a hard saturation current where the inductance quickly falls to a small percentage of the 0 amp inductance. All power supplies contain capacitors on their input and output. A capacitor is a passive element that stores energy in an electric field and resists changes in voltage. A capacitor acts like an open circuit at DC voltage and a short circuit at high frequencies. The capacitor's main function is to provide AC current filtering and voltage holdup in power supply applications. There are several capacitor considerations that require attention when designing your power supply. The value of capacitance is critical to consider for two main reasons. First, during the off time of the control switch, the capacitor holds up the output voltage as the energy in the inductor decreases. Therefore, the amount of power supply ripple is directly related to the amount of output capacitance. And second, when the load current of the power supply suddenly changes from light load to heavy load, the capacitor must support the extra current while the current ramps up in the inductor. A common example of this is when the lights in your house briefly dim when your washer or dryer turns on. The DC voltage rating specifies the maximum voltage that can be placed across the capacitor terminals. Several types of capacitors, including tantalums and aluminum electrolytics, can be severely damaged if this voltage rating is exceeded. Pay attention to voltage excursions during transients events as well. DC bias is a common consideration in ceramic capacitors. The amount of effective capacitance provided by the ceramic cap decreases as the voltage across it increases. ESR and ESL are parasitic components in series with the capacitor. The ESL limits how fast current can change in the cap and is a limiting factor in transient response. ESR also affects the voltage dip during a transient event due to IR drop. In addition, ESR also limits the RMS current rating of the device. As the RMS current increases, the losses in the capacitor due to I²R increases. Lastly, dielectric material and lifetime are important considerations. Capacitor failure due to exceeding the number of hours of operation is one of the most common failure mechanisms in consumer electronics. A diode is a two-terminal device that is used for rectification and is common in both AC to DC and DC to DC power supplies. It acts like an electronic version of a check valve, allowing electric current to pass in one direction and blocking current in the opposite direction. To pass current, the anode, represented by the A terminal in the figure, must be at a higher potential than the cathode, represented by the C terminal in the figure. When this happens, the switch is closed and current moves from A to C. The flow of current causes a voltage drop from anode to cathode and can be on the order of about 300 millivolts to 1.2 volts. This is called the forward voltage. The forward voltage times the forward current determines the power dissipation in the diode. Care must be taken to ensure the power loss in this component does not exceed its rating. To open the switch, a reverse voltage is applied from cathode to anode. There are several different types of diodes, including PN, Schottky, and Zener. Each of their uses is specific to the type of application. Important diode characteristics, including forward voltage, current rating, reverse voltage, and reverse recovery, are just a few to consider in your design. A metal oxide semiconductor field effect transistor, or MOSFET for short, is a three-terminal device with terminals drain, gate, and source. The MOSFET is by far the most common transistor in digital and analog circuits, replacing the ever-popular bipolar junction transistor, or BJT. Power supplies use MOSFETs for switching voltages and currents and can act as both control switches and synchronous rectifiers. The two types of MOSFETs are N-channel and P-channel devices. An N-channel device is enabled when there is a positive voltage from gate to source that is greater than the MOSFET's threshold voltage. When this occurs, the drain is connected to the source and current is allowed to flow. A P-channel device has a similar operation with the opposite orientation. The P-FET requires a negative voltage from gate to source, in this case less than the threshold voltage, to connect the drain and source terminals. One interesting property of both NFETs and PFETs is the presence of a body diode between the drain and source terminals. If the anode is at a higher potential than the cathode for either device, current will flow regardless if the gate to source threshold is exceeded. However, when the gate is charged and the channel is active, the on-state characteristic is resistive and the forward drop of the channel will be less than the forward drop of the diode. Therefore, most of the current will flow through this channel. There are many trade-offs and design considerations in MOSFET selection, including price, size, and performance. Performance characteristics such as voltage rating, RDS on, gate charge, and output capacitance are just a few that must be considered.